Okay, so we'll get started on this. And so we're going to be doing the selection rules for rotational transitions. Thanks. Switch over to laptop. Come on. And show screen. Yay. Last time we looked at the symmetry of those rotational wave functions. And so today we'll look at the combinations for the transition dipole moment to solve for the symmetry selection rules. So you remember this, we did for the 1D particle in a box, we solved for those selection rules using symmetry. And then here for the particle on a ring wave functions, we looked last time at ways to depict this wave function. So on the left, we could spread that ring out to plus or minus 180 and look at them sort of in one dimension with the wave function deflection on the y-axis. We could show them wrapped around the ring. We kind of talked about that. Or we could show them top down as these little, looks like little pie wedges, Trivial Pursuit type pies here. And we've got the pluses and minuses indicating whether that wave deflection is above or below the ring as we've plotted it here. Now, above or below the ring, I'm not quite sure I actually like that because the ring's not necessarily vibrating like that. We could think about this like we do with the electron cloud as deflections out and in. So in this case, let's think of this as the ring deflecting out here and in here. Okay. Now we have in our mind, in our language, it's a particle on a ring. We call it a rigid rotor. And so the classical view of that is a particle rotating around the ring. But if we're thinking about something rotating around the ring, what is the wave function? Right? The particle is sort of in all space at all times. So it's the wave function kind of smears that particle around the whole ring. And so it's hard, when you're talking about the wave function, it's hard to see the rotation. Did you see that? Do you understand what I'm saying there? Yeah. And so just like the spherical harmonics, the atomic orbitals were the harmonics of a hollow sphere, these wave functions are the ring harmonics. These are the harmonics of a ring. And so these are the standing waves that you get when you have a ring system and how it vibrates. And so if you hit this, you hear the tone. So I don't know which wave function. If I had a high-speed camera, I could look at this ring and see it deflecting as it vibrates. And that's my best analogy that I can come up with these wave functions, is that you'll have this vibration of this ring, and this vibration of this ring will have certain symmetries associated with its wave function. Now, how that's rotation, right? Because there's no location of the particle, really. You square the wave function, and the square of the wave function is defined as the probability distribution. That's an axiom. That's something that's really not provable. Okay, that's just what Schrodinger started with when he solved these systems. And so this is, so you would say, well, if we were to square this wave function, the particle is here and here. There's a 50-50 chance of it being found on either side of that ring, and a 0% chance to find it here and here, at least in its real part. Okay. So anyway, just some more conceptual discussion about these pictures that we're drawing. We put this in the point group. We went through the flow chart and came up with D-inf-h. And so then we have the D-inf-h character table. And then we notice that as we go up in quantum number, that we essentially have these symmetries for our different wave functions. So now we know our symmetries. This n equals 0 is A1G. The n equals 1, we have an E1, and it's U. You look at the plus and minus over here, you know it's a U. And then this is E2G. We just reviewed a little bit, okay? So you haven't missed anything. Okay? All right, and then the next one is what? E what? E3, and then you look at the pluses and minuses and you see that it's a U. And so all the odd ones are U and all the even ones are G. So the next one is E4, G, then E5, U. It just keeps going up and up and up. E6G. So now we know, and we can go up to, you know, infinity. I mean, we just keep counting and adding up G's and U's, and the quantum number is the subscript. And then light, if we're going to interact this with XY light, and we're really going to only focus with XY light because this is a two-dimensional system. It's in the XY plane. And so that's really the only light that can interact with it. There is no Z-axis in this system. Okay. So when we do the selection rules, those are the only photons we're going to bring into as XY polarized light. So it's just that E1U. So here are our wave functions. This is the energy level diagram. And so what we want to know is with this XY light, E1U, what are the selection rules, right? Do we change by 1 quantum, by 2, by 3? Is it like the particle in a box where we can go to all odd transitions? Is it like Raman where we can go to even transitions? Or is it even more restrictive than that? Okay. So let's focus on this. We're going to use the direct product table. And this was part of the work that we had to do for that paper for CHEM Ed, was to extend the direct product table for D-inf-h. It stopped in all the sources that we could find. It stopped right here. So that was the end of the direct product table that we had. And so we had to actually build out the rest of the direct product table. And I think that's part of one of the services of that particular article. Let me make sure I'm recording this because I want to make sure this. Yeah, okay. Just double checking. Okay, so that was one of the things that paper did. I think it made a contribution. If people need an expanded D-inf-h direct product table, they can get it from that paper that Victoria and I wrote. Because what's missing here, we have the E1 times E2. So we had adjacent products, like you see what I mean by adjacent. This is 1 and 2, but we didn't have in this smaller table anything related to the higher jumps, like 1 to 3, 1 to 4, 1 to 5, 1 to 6. We had no idea how those things behaved. And so we had to figure out what this was. You know, when I take E1 times E3, or when I take E1 times E4 and E1 times E5. And you notice some interesting patterns. When I take E1 times E2, I go down and up. You see that? E2 becomes E1 and E3. And when I take E1 times E3, it goes down and up as well. It goes down to 2 and up to 4. So it kind of splits them to adjacent levels. Thinking of these E's as levels, because again, if we look at our wave functions, well, here they are right here. If we look at our wave functions, you know, we have E3 here, and it's between E4 and E2. So we operate on E3, we split it to E4 and E2 in this direct product table. If we operate with E1 on E4, it drops to E3 and goes up to E5. If we operate on E5, it splits to 4 and 6. E6, it splits to 5 and 7. And so we were able to fill that out. So we widened the table. And then what does it happen? What happens when we go down? So let's look at E2 times E5. Okay, E2 times E5. Notice it goes down 2 and up 2. So when we bring in a 2, it splits it by that amount. What if we do a 3? E3 times E5, again, it goes down 3 and up 3. So we were able to verify that this pattern operates all the way around. So we come in with 4 times E5, it goes all the way down 4 and up 4, so 1 and 9. And so we verified this trend all the way through the table, and then we were able to complete the table. And now this is enough of the table that you could extend it easily, you know, to infinity, you know. And then we had to verify that this, what happens in this square, right? What is this little e? Okay, so E1 times E1 is E2 and A1 and A2, but what is E2 times E2? You know, is this E3 or E4? Right? Does it go up by 1 like it did here, or is it 2 times that? You know, is this 1 plus 1 is 2, or is this 2 times 2, 4? And it turns out that it's 2 times 2, 4. So here again, or no, it's plus. 2 plus 2 is 4. Here's 3 plus 3 is 6. Here's 4 plus 4 is 8. And so we were able to work on the diagonals, and we finally figured that pattern out as well.
So you went as far as E6, and then you made not the assumption, but so you're saying that so E7 times E7 would act the same as E6, E6, and so on and so forth.
Yeah.
So it's a pattern.
Yeah, we needed to see if that, what kind of patterns were there in the direct product table.
Okay.
And so I'm not showing you that work, but that's what Victoria and I did to expand this table. I had to cut something, so I just cut us making the direct product table, and so I'm just giving you the direct product table. Okay, but I'm just showing you some of the effort that went into it. And it was those cosines times cosines. Why does it split? Well, think about this. These wave functions are, the real parts are cosines. And so here you have a cosine of 2 theta times a cosine of 3 theta. And what is that trigonometric substitution? It's that you get a sum of 2 cosines, cosine of 2 theta plus 3 theta, and a cosine of 2 theta minus 3 theta. So it takes that 3 and splits it, plus and minus 2, inside the cosines. And so what we're seeing in this direct product table is actually a result of that trigonometric substitution that you get when you multiply these cosines together. So that's pretty cool. I mean, you can actually see, and that's how we verified these patterns, is using those trig substitutions, where you have 2 cosines multiplied by each other. You end up with a sum of cosines with the differences and the sums inside the parentheses. Okay. Now we can do the GU symmetry rules very easily, because we know if we have light, which is U, and if we end up with an odd number of U's, then it's forbidden, right? Because we're going to end up with a U in the end. And so if we have, again, if we have G level to G level, that's going to equal 0. And if we have U to U, that's going to be 0, because this is an odd number of U's. And so if you're ever taking a quiz or a test and you see a transition dipole moment integral and it has an odd number of U's, when you do U times G and G times U and U times G, you're going to get down to the bottom and you're going to have a U. And so it's going to be 0. It's an odd function. Integral over all space of an odd function is 0. And so you know that those transitions are going to be forbidden if you have an odd number of U's. Okay, so we know that this... So we know that jumping by 2 is forbidden. So that's not allowed. And jumping from U to U is not allowed. You see what we're learning here with the direct products here. We also can't jump up by whatever this is, 4 minus 0. So we can't go by 4 either. So we can't have any even jumps in our energy leveled diagram. We can't jump by 2 or by 4 or by 6 or by 8. So we know that those are out. Okay. Now let's look at just sort of individual jumps, quantum jumps, and see if we can determine a pattern. So let's look at the n equals 0 to n plus or minus 1. So we're going to look at this one here. We're going to see if this is allowed. Okay.
Why is light always E1?
Because of the direct product table. So good question. Let's go back here. Not direct product, character table. So in the character table for D-inf-h, we come down here and we find xy. And so that's the light that's coming in. That's the middle part of our transition dipole moment integral. And so it's always E1U. That's the symmetry of the xy light.
So we don't look at the Z light?
We don't look at Z light because this is a two-dimensional system. It's one dimension in the theta, right? So it's a one-dimensional system, but in terms of light coming in, interacting along the x axis or the y axis, that kind of makes it a two-dimensional system. And so the symmetry of that x or y polarized light is E1U. Yes?
Is that for all D-inf-h?
Yes, this is for all D-inf-h, so even for molecules. Now for like CO2 or something, we have a z-axis. It's a three-dimensional system because you have, the 3 dimensions of the molecule. But we're just talking about rotation around a ring, sort of fixed in space. There is nothing on the z-axis at all. So we only have rotation in the xy plane, and so that's really the only light that can interact with our system. Okay. All right, so we're here we're checking the so this A1G to E1U, so this goes here, the A1G goes here, and this is light. So we can think of this this ring and light's coming in, you know, in the same plane as that ring, and can it cause this transition to occur? Okay. And so here's the pictures over here. You know, we have, if we want to shade one of these, let's say we shade the negative one. We're going from, you know, unshaded to shaded on one side. Can we do that? So A1 times E1 is E1, and G times U is U. And then we go up here to the character table, and we see E1 times E1 is right here. You know, A1, A2, and E. And then the G, it's U times U, so we get G's for all of those. So we have A1G in the result, and so this is not equal to 0, so that's an allowed transition. Now that one's pretty easy because we have A1G as our ground state. Now it gets a little more complicated because we have E1 and E2 and E2 and E3 and so on. So we're going to be hopping around this direct product table. Any questions about this before we move on? Okay, so now let's look to see if we can go from E1U to E2G. So this is now this transition here. Is this one allowed? Okay. And so we have this E1 times E1 gives us A1, A2, and E2. And then U times U is G, so we have G's for all of those. And now I've color-coded this so that we can see that E2 times A1 is these first two, and E2 times A2 is so see over here we have E2 times A1 is E2, E2 times A2 is also E2. So those are the first two orange ones in that sum. And then we have, it's G times G, so we have G. And then lastly, we have E2 times itself. So that's where we get A1, A2, and E4. So that 4 comes from this one right here. So you just work your way through the direct product table and come up with your sums. And then because this has A1G in it, it's not equal to 0, so that's an allowed transition. Fantastic. I just want to make sure you ask questions, because a lot of folks will ask questions after class or on email, and so ask now, so that, because you should be able to reproduce this. If I say, show me the symmetry selection rules that, you know, show that this is an allowed transition, you should be able to do everything on this page if you're given the direct product table. Okay. All right, let's do another one. So now we have the 2 to 3, so we're going from 2 to 3. So we have E2G over here on the right, E3U here, we have light in the middle. So we have E1 times E2, that gives us that intersection there. So it's a sum, it's E1U and E3U, because it's U times G, so we have U's on both of those. And now we have E3U times each one of those terms. So E1 times E3, so we have this E3 and E1, that's this orange intersection up there. And so that gives us those first two terms, the E2 and the E4. Okay. And then over here we have the E3 times the E3. So we find that intersection, that gets us A1, A2, and E6. So does everybody see where the E6 came from? Right there. But the main thing we're looking for is that A1. So anytime you get something times itself, if you'll notice on that diagonal, there's always an A1 in that sum on the diagonal. And so we have an A1G in there, and so this is not equal to 0, so that's an allowed transition as well. Okay. Hopefully you can see the pattern. If this is a 2, and this differs by that +1 or -1, when I take this E1 times whatever number this is, it's going to split it up and down. And if it splits it up and it's a 3, and this one's a 3, we know we're going to have an A1 because we're on a diagonal. We're on that diagonal of the matrix. And so if you didn't follow that, we'll do the general case here in a minute. Okay. Now we're looking for 3 to 4. So we'll just do one more of these. E3U, E4G, and light in the middle. So E1 times E3, notice how it takes that E3 and splits it into 2 and 4. And it's the 4 that matches where we're going. Okay? And because that 4 matches where we're going to be on the diagonal, we're going to have an A1. What if we were doing E3 down to E2, like an emission? Okay? So the 1 times the 3 would split it into 2 and 4, and 2 is the lower level, so it would allow emission as well. So anything adjacent to the level you're on, you're going to hit because of the E1 operator in the middle. I think that clicked for some folks. Okay, so anyway, E1 times E3 is E2 plus E4. U times U is G. And then we'll multiply that E4 times both of those pieces. E2 times E4 gives you, yeah, E2 and E6. And then E4 times itself gives the A1, A2, and E8. Okay. Yep, and we have the A1G not equal to 0. Notice we didn't do any of the G to G or the U to U's because by categorization, there was the odd number of U's. So we're not even going to test those because we know by G and U symmetry, those are not allowed. Okay. Now, we haven't done the change from like n equals 0 to n equals 3. So like a change of 3 quantum numbers. Okay, so let's see. So 1 to 4. So here we're going from 1 to 4. Let's test this one because, in the particle in a box, this one is allowed because it's just odd and even symmetry in a particle in a box. But now we have this rotational symmetry with this rotational quantum numbers, and it's not, A1G, A1U, A1G, A1U. It's not like AG, AU like the particle in a box. So we have over here E1U, and up here we have E4G. Now, before we even do the problem, think about what E1 does. So that light operator operating on the state that we're in, E1, it's going to split it up and down. Okay? And when it splits it up, it's going to make it an E2. That's not E4. It's not going to split it and get us up to an E4. So this seems more restrictive. So let's go ahead and do the math. E1 times E1 is A1 times A2 plus E2, and U times U is G. And there's nothing in that sum that matches E4. So we cannot get to a diagonal which contains A1. So we have E4 and E4, those are G's. And then we have the E2 and E6, the E4 times E2. And so, sorry, there's no A1, so that's equal to 0. So this is different than the particle in a box, where you have all odd jumps allowed. Delta n equals plus or minus 1, plus or minus 3, plus or minus 5. This rotational selection rule is restricted to just plus or minus 1. Okay, and we'll do the sort of general case next, but this shows that we can't jump by 3. And that also means we can't jump by 5 either, or 7 or 9. The only thing we can do is jump to the adjacent level, because that's all that E1 operator of light is going to do. It's going to split the level it operates on, up or down. And we can go down by 1 level or up by 1 level. Okay. So let's look at the general case to see if we can understand the general case in using the direct product table. So we have these general selection rules. So we're going from, any level of En operated on by light, and light is E1U, and we're just going either up or down to E plus or minus 1, right? And so whenever light operates on En, notice how it splits it. It goes to En minus 1 or En plus 1. Mm-hmm. So like if light operates on E3, it goes down to 2, that's N minus 1, and up to 4, that's N plus 1. Everybody see that? Yeah? Okay. And that has to match this for it to be allowed. And so if we end up with one of these, matching, then we're good. And so this is the general case. When I take the En plus 1 times En minus 1, we get a 2 and a 2n, and then we get En plus 1 times plus 1, we get these. If it was the minus 1 times the minus 1, we get these. And so you can verify these general results where we end up with the A1. Now where are the G's and U's? Well, we know that light is U, and so we either have one of the ENU or En plus 1 has to be U. So
you have an even number of U's.
Yeah, you have to have an even number of U's. Okay, and so this ends up being the only way you're going to get an allowed transition is if we have a change by the quantum number plus or minus 1. Okay. It's kind of hard to see with the general case. So I think we were able to see it. I noticed more nods when we were on this scene here with the numbers. Okay. But as I showed the ends plus or minus 1, I think people were like frying their brain cells. So you can look at these cases here and verify these in E2 and E2N and so on with the direct product table. Okay. So let's look at Raman. Now, what's interesting about this, though, this rotational symmetry, is that was what they just brought angular momentum in out of the blue. They did symmetry selection rules for other kinds of spectroscopies, but when we got to rotation, they said light has 1 unit of angular momentum. Therefore, we have a delta N or delta J, if using the rotational quantum number that's traditionally used, J. They say it can go up or down by 1 unit because light has 1 unit of angular momentum. Okay, we verified that using symmetry, so we got the same answer. That's a good thing. That was the thing that made us say, "Hey, we proved it." We got the same answer we get using the angular momentum argument. So then we said, "What about Raman? Let's see if this works for Raman." So what are the symmetries of the polarizability operators? We go back to the D-inf-h Character Table. And it's those squared terms, the ones not including Z, because once again we're just in the XY plane, and so we could have the x squared minus y squared, or we could have the XY. So we could have 2 photons of light coming in and scattering off this rotational system. So our Raman polarizability operator is an E2G. Okay. So right away, this means we have to connect either 2 G levels or 2 U levels, because we have to have an even number of U's. So we know it's going to be at least jumping by 2 quanta or 4 or 6. Okay. Adjacent quanta would have only 1 U involved, and so we can't have adjacent levels jumping. Now that's, again, the Raman has 2 photons, and so we typically talk about 2 units of angular momentum. It can go up by 2 or down by 2. And so this looks like this is going to work out the same thing. So here we have this XY type of light interacting with our lower state, En. And so we're going to have, if we have 1U or 1G, we know that that's going to equal 0, right? No matter what it is, because of the GU symmetry. Also, if we have the other, if we have this opposite case where the lower state is U and the upper state is G, that's going to be equal to 0. And so G to U and U to G are forbidden. And so we know that the selection rules are not 1, 3, 5, 7, 9. Is everybody clear on that? That seems straightforward, right? Okay, so now let's walk through the general case for Raman selection rules. Okay. So if we have an E2, look what it does to the En. All right, so E2 comes up here. Let's just take this case of N equals 3. So it goes down by 2 and up by 2. And so for that to be allowed, we need to connect it to a level that's up or down by 2, so that we'll have something times itself. Anything times itself is going to contain A1. So if we have E15, if you can get it to work out, we're at E15 times E15, then we know the result's going to be A1 plus A2 plus E30, I think it is. E30. Okay. So let's take E3. So we know that it goes down to 2 and up to 2, up by 2. So we end up with a E1 and E5. And so we have a possibility of an E1 on the left. If we have an E1 on the left times an E5, we end up with E4 and E6. If we have E1 on the left times an E1, we end up with that A1, A2, and E. So this could go from a 3 to a 1 and be allowed. It could also go 3 up to 5. Okay. If it goes up to 5, then we have an E5 times an E5, which gives us an A1 plus an A2 plus an E10. So if we're at level 3 and Raman light comes in, it could do a Stokes scattering. It could interact and cause that quantum state to jump up to the E5 level. And the photon would come out with less energy because the system has upped its rotational speed by 2 quanta. It went from a 3 to a 5, and that's allowed. It could do an anti-Stokes. So the photon could come out with more energy because the system went down from an E3 down to an E1 and gave that excess 2 quanta of energy to the light photon as it left the system, and now the light is blue shifted. It's got more energy. That's what we're talking about. Raman scattering is inelastic scattering. Photon comes in, interacts with the system. If the system goes up in energy, the photon leaves some of that energy behind and comes out red shifted. That's Stokes scattering. If the photon comes in, interacts with the system in quantum state 3, and the system drops to quantum state 1, that extra energy goes into the photon of light and it comes out with more energy. It's blue shifted, shorter wavelength, and that's anti-Stokes Raman. Okay. And we've solved the general case here. If we come in if light's represented with an E2, we know then we can jump up and down 2 levels, and that's it. That's the only shifts we can make. And so our quantum selection rules, our spectroscopic selection rules for Raman are plus or minus 2, which matches the experiment as well. Did everybody understand this general case? So whatever this E is for light, right here is your selection rule. And it ends up being that simple because of the direct product table. Okay. And because XY polarized light was E1, we had the selection rule plus or minus 1. If they came up with a new spectroscopic technique, okay, the Williams spectroscopic technique, and it had some funky interaction with light, maybe might be dark energy or something exotic like that, right? And it was E4 symmetry. Then the selection rules would be delta N equals plus or minus 4. Yeah. Because E4, when you come in and you multiply E4 times, let's say you're in quantum state 5 here, when you operate on that, you're going to get 1 and 9. And so it could drop down to quantum state 1 and be allowed, or it could jump up to quantum state 9 over here. And when you have 9 times 9, then you're going to get an allowed transition. Okay? So it's that simple. It's just what the operator is tells you what your selection rules are going to be. And it's pretty neat. And so with the angular momentum, if we go back to the yeah, here we go, the character table. Notice this cosine, this thing in the middle is called a frequency factor. You know, if you're just dealing with cosines and frequencies, this is the frequency factor. This is twice the frequency, 3 times the frequency, 4 times. That is if you think of the classical model of rotation, it's twice as fast, 3 times as fast, 4 times as fast. Okay, it's 1 unit of angular momentum. So this quote cosine term in here, this is angular momentum. And so when we have light, it has 1 unit of angular momentum. 2 photons has 2 units of angular momentum. Okay, and so if we have a quantum state here, that's 1 unit of angular momentum. If we go up 2 levels, that's 3 units of angular momentum. So this change in quantum states is a change in angular momentum. It's a change in velocity of rotation. Okay, so this is just, I really like the rotational system. It's fantastic. I mean, the vibrational, or the particle in a box, that's a pretty cool system too, because it's a string, right? A guitar string or a violin string. You pluck it and it vibrates, right? You can see that visually. But this also is satisfying too. If something is a cosine 2x, it's spinning faster than a cosine 1x. Okay. Now we can show this visually here with these wave functions. And so here's what we show with some of these, we have a change. We have this quantum state 0 going to quantum state 1 in these vibrational wave functions. And you can kind of see that these patterns match here. And so anyway, the Raman, you can think of it as a photon coming in on the X and going out on the Y, polarized light, and giving us this pattern. And that's connecting 0 to 2 and so on. So this is the graphic that we made for our paper for the abstract graphic. So that's it for this set of selection rule analysis on rotational systems. Are there any slides that you want me to clarify?
You just got to practice doing the products, doing that.
Yeah, this is probably the best page here to kind of explain how things go because of the arrows, right? But yeah, just work your way through it. If you'd like to, really, if you want a challenge, try to figure out if I've made any mistakes here. I don't think I have, but try to figure out where I got these numbers right here, these trends, because I wrote down these general trends, and I believe they're right. So you check my math, and that'll force you to really dig through it, okay? So you see where I got this 4 and 2n and 2 times n plus or minus 2, okay? It was pretty late. So I can't say that it's perfect, but you want to check my work, that'll definitely be a good thing. And then to prep for on Friday, if you would, I'll make sure I put a link in Blackboard, but watch that video on peak picking and regression analysis, because we're going to be talking about that on Friday. Okay, so I'll make sure you have those links. It's just, I think the peak picking, do you remember how long it was? Like 40 minutes?
For the video?
Yeah.
I think you had 2 different videos. One's pretty lengthy and one's not too bad.
Yeah, the first one, the peak picking one, is pretty lengthy, but it's pretty tedious. I mean, I go through the whole thing, and so you can skip ahead. Once you figure out what I'm doing, just like jump ahead in the video, and you'll see I'm doing the same thing through the whole video. So you don't have to watch all 40 minutes, right? But then the linear regression, definitely watch that one. Okay, for sure. And then I'm going to also post a link to the propagation of uncertainty video. because you need a refresher on that to make sure that you understand how we propagate uncertainty, because we're going to need to use that to understand the uncertainties in our bond lengths and our force constants. Okay, so
are you going to give us an Excel sheet, a pre-made one?
I'm going to give you the peak-picked data, and I want you to do the regression analysis and the uncertainty analysis. So it's just that last part, just that analysis part, because I want everybody to learn how to do linear regressions and understand p-values and those kinds of things.
Okay.
But as far as the tedious 2-hour job of peak picking, we can skip past that. Okay. All right, so that's a good place to start.